I'm Chet Haase. I work on the framework team on the Android team at Google. I work on animations and all kinds of graphics stuff. What excites me about the platform is basically all the same stuff. Doing graphics for mobile devices, very cool stuff. How to improve the user experience and make these devices and the applications better and more exciting.
My name is Romain and Chet. I work at Google on the Android UI Toolkit team. It's also the framework team. I've been working on the UI Toolkit, some SDK tools, animations in the past. I've been doing graphics, the launcher, live wallpapers, a lot of stuff. I've been on Android for 4 years now. And I love it because it's challenging. We have those tiny devices and we have to make really cool stuff working all the time in your pocket. So extremely cool. So good evening everyone, this is Chet Haase. He loves to make jokes, so please laugh because they're not always funny. And I am Romain and Chet. We both work at Google on the Android team, and more precisely we work on the Android framework team. We work on the UI Toolkit. Chet is in charge of animations, and I do a lot of stuff. I don't even remember what I've been doing this week, but everything that's related to graphics and UIs and widgets, things like that. So tonight we're going to talk about graphics and animations first. We're going to have a quick overview of our graphics architecture and some cool APIs that you can use to make your apps look better. Oh, and because we're so cool, you can also follow us on Twitter. We're both still figuring it out. Chet, I think, still doesn't understand how to use it, so he doesn't post much, so you can follow him, make him happy, and it won't bother you much. Okay, so our agenda for the first part, like I mentioned, graphics architecture, then we're going to talk about graphics APIs, and then we're going to talk about animations. So I like the first part because it basically explains everything that the documentation does not explain. And most of what you're going to see in this section, a lot of people on the Android team are not aware of because it's not something they deal with a lot. But when you write an application, you will probably run into those issues that forces you to learn about graphics. And with those few slides, you should be able to understand everything you have to know. So before we get started with the fancy diagrams, I need to explain a few keywords that are related to the Android platform. So when we talk about canvas, we're talking about a 2D drawing context. The canvas is an object that you use to draw on screen or that you use to draw into an off-screen bitmap. Skia is the name of our 2D drawing API. So if you're familiar with Swing, for instance, you might have used Java 2D in the past. Skia is our equivalent of Java 2D. You will also find it under the name SGL for Skia Graphics Library. It's the exact same thing. We also use OpenGL a lot. I'm sure all of you know what OpenGL is. We use it for 3D, for instance, in games, but we also use it in the system for 2D rendering. So for instance, the window composition in the system is done with OpenGL, but we'll talk about that later. RenderScript is an upcoming technology that's actually already on your phone if you have an Android phone. If you have live wallpapers, they were built using RenderScript. This is not a public API, but the idea behind RenderScript is to have a language that's targeted at graphics. It looks like C, it's not quite C, it's compiled on the device. It has advanced features like support for matrices and vectors in the language. It supports multiple cores directly, so in the future if you want to run your RenderScript code on the GPU or on multiple cores, it will work without you having to do anything. So it's a pretty exciting piece of technology, but it's a lot of work because it's a new language, it's a new compiler, it's new APIs, it's new drawing APIs. We're starting to build a scene graph with it, so there's a lot of things still to be done. So I can't promise you when it's going to be available, but if you're interested in knowing more about it, you can look at the source code of the Android platform. If you look at the source code of the live wallpapers, you will see examples of RenderScript. You can also look at a talk I gave last year at Devoxx. I think it was about resolution independence and the future of Android graphics. And I did half an hour on RenderScript showing examples and giving more details about what it's going to be. Oh, and RenderScript can also act as a very, very, very nice replacement for JNI, which is a good thing because JNI kind of sucks. Surface. Surface is basically a drawing buffer. Every window in the system is backed by a surface. It has various names on different platforms, but it's just a buffer, it's just a bunch of pixels. Surface Flinger is the name of the window compositor. This is what moves the windows around, do the fancy fade effects when you launch an application. It's a really nice piece of technology, and we're probably going to do some fancy stuff with it in the future. And Pixel Flinger is also something really nice. Actually, you're probably using Pixel Flinger a lot if you run the emulator. Pixel Flinger is basically a JIT for graphics. So we have a software implementation of OpenGL, and it's using Pixel Flinger to generate bytecode, actually assembly code in memory at runtime based on what the device is doing. So this gives us nice performance with the software version of OpenGL. So when you use the emulator, because we don't use the hardware acceleration part of your laptop or your desktop, we use a software implementation of OpenGL on top of Pixel Flinger. Finally, View and View Group. If you've already written an Android application, how many of you have ever written an Android application? Raise your hands. That's pretty good. All the other, shame on you. So a view is called a widget or a control. It has various names on different platforms. We call it a view, and View Group is just a container of views. Surface View is a special view. It's a little special, like the name suggests. It's related to surfaces, and we're going to talk about it in a later slide. So this is the basic graphics architecture of Android. So on top, of course, you have your application, and you will have 3 different ways of rendering stuff on screen. So you can use the canvas, like we talked about, and the canvas relies on Skia, our 2D drawing library. Or you can use RenderScript, and RenderScript itself for now relies on OpenGL. It doesn't have to run on OpenGL, but this is currently the implementation. Or you can use OpenGL directly. But whatever you choose to draw, you will draw in a surface. The surface is created for you by the system. You have very little control over the surface. You can choose the quality of the surface that you want, 16 bits or 32 bits, is it transparent or opaque. But other than that, you can't really control that surface. OpenGL, so we have support for OpenGL ES, that's for embedded systems, I believe, probably. 1.x extra special, 1.x and 2. So there are 2 different implementations of OpenGL. I mentioned the software implementation on top of Pixel Flinger, and that one is limited to OpenGL ES1. So if you use the emulator currently, you have to use OpenGL ES1. You can't use OpenGL ES2 in the emulator. You have to use device. But if you have a device with a GPU, depending on the device, you have support for OpenGL ES1 or OpenGL ES2. Pretty much any device that was released after the Motorola Droid 1 year ago should support OpenGL ES2. OpenGL ES2 is very different from OpenGL ES1. If you're not familiar with them, I won't go into the details here, but they're very interesting to learn. Now, so I mentioned Surface Flinger. So the role of Surface Flinger is to, like I mentioned, compositing windows. So at the top here, this is the first diagram we saw. That's your application drawing into a surface. And all what Surface Flinger does is take all the surfaces that are currently active on the system, actually the surfaces that are visible, and this is determined by the window manager, and simply composes them in a single frame buffer. So Surface Flinger, to do its job, uses either OpenGL or a 2D bleeder. So the first Android phone that was released, the T-Mobile G1, was using a 2D bleeder that was called the MDP. There was a special 2D engine, a hardware chip that could do 2D really fast. Aside from the T-Mobile G1, I think everything else uses OpenGL. And so once again, because it's OpenGL, it either relies on the GPU or on Pixel Flinger. So in the emulator, we're going to use Pixel Flinger. On an actual device, we're going to use OpenGL. Views. This lovely diagrams explains how drawing views work. This is something that you will probably have to deal with if you write an application, especially if you write custom views or custom view containers. And this shows the life cycle of a drawing event. So all the blue arrows here represent what we call invalidation. When you call invalidate on a view, it means that this view is dirty and you want it to be redrawn on screen. So let's imagine here that we have a view at the bottom of our tree that calls invalidate. It goes back all the way up to the top of the tree where we have something called a view root. And the view root is basically where everything happens for the UI. This is where we dispatch the key events, the touch events. This is where layout happens, and this is where we start the drawing sequence. So when the view root receives an invalidate message, it asks the surface of the window that contains all your views for canvas. So for that, we call a method called lock canvas. And I mentioned that here because it's an API you can use yourself when you use a surface view. Once again, we'll come back to surface view a little later. After locking the canvas, the view root calls draw and passes the canvas on all its children. So the role of your view group when it receives a call to draw is just to call draw on all of its children. And when that's done, we unlock the canvas and we swap the buffers. Every window on Android is double buffered. So the call to unlock and post will swap the buffers and display on screen what we've just drawn. So this is so that diagram came to be because I see this question come up very often on mailing lists and groups. People wonder how they can force a view to be refreshed. So if all you want is change the display of the view, you have to call invalidate. If you've changed properties of the view that will affect its size, you have to call request layout. The two are independent. Calling request layout will not cause a redraw, and calling invalidate will not cause a relayout. View groups. So that's a quick explanation of the different drawing methods that you can use and override when you write a custom view. So once again, let's imagine that you have a view group here and it calls invalidate, so it goes back up to the view root. The view root calls a method called scheduled traversals that will start the next drawing sequence. And we put that here in the diagram because if you have exceptions that happen during in a draw method and you look at the stack trace, you won't necessarily see the code of your app. You might see that the root of the exception will be scheduled traversals. So if you see that method, it's perfectly normal. That's how everything happens when we draw. So scheduled traversal, we call the draw method to be called on view group, and view group will basically perform 4 operations. It will first draw its background, and the background is what we call a drawable as a draw method. So we have bitmap drawables, we have color drawable. There's a bunch of different drawables you can use, and they can be declared from XML. After drawing the background, we call onDraw. So the role of the onDraw method is to draw the content of the view group itself. And when it's a view, we only call onDraw. Then we call dispatch draw, and the role of dispatch draw is to call draw on all the children. To do that, the view group will call draw child, and this is where we handle, for instance, animations, transformations, stuff like that. So if you look at the stack trace during draw, you will probably see draw child, dispatch draw, onDraw, draw, and then somewhere up the scheduled traversals. Surface view, so I talked about it a couple of times. A surface view is a very special view that gives you access to a surface. So the way it works, and you can see here that we have a view root at the top with its own surface, so that's the drawing buffer of your window. And if you put a surface view in your UI, we will give you a surface that you can manipulate directly. And the way it works is like this. So let's imagine that this lovely galaxy here is actually a surface view. A surface view itself doesn't do much. It basically tells the system that it wants to have a transparent hole where it lies. And the system will put the surface view surface behind your own window, and you will see it because the surface view just leaves this transparent hole. So that's to give you an idea. You have your window here, and all this area here is basically the surface view, and you just see through onto the underlying surface. This is why, so surface view is extremely efficient because you control drawing. You don't have to go through the invalidate and draw mechanism. You can create your own thread. You can draw whenever you want. When you draw something into the surface, it does not get cleared automatically by the system. It stays there until you decide to clear it. You can change the format. You can change the size. The biggest limitation is that you can only have one surface view at a time in a single window. So a view root can have only one surface view child somewhere in the tree. And surface view, very important, I forgot to mention it, that's how you do OpenGL in your application. If you want to use OpenGL, if you want to write a game, for instance, you put a surface view in your application, and when you initialize OpenGL, you can give it a surface, so the surface from your surface view, and it will automatically become an OpenGL rendering buffer.
So this is, yeah, as a precursor to talking about how we do some of the graphical effects in the API. So I wanted to write a simple demo that showed a couple of different effects here. So it's a simple picture viewer. You've got these thumbnails down at the bottom, so you can select another thumbnail, and then it shows up there all this stuff that we all expect in a picture viewer. A couple of things to notice are the effect that we have for the reflection, which Romain will talk about in a few minutes, and then some effects down here as well. This is, I was going to some great effort to create a layout and automatically do scrolling and some animation when I selected these things, and then I discovered that there's a widget called Gallery that just does it for me. So that's really cool. But then I added an animated effect to, because I thought it's good. So I tend to think maybe some would say too much about animations, but I like them because they are a great way to give the user an indication of what's going on in the UI. So in particular, when you want to select an image, it's nice to give the user an indication, well, this is the currently selected image. And instead of having these abrupt changes in the UI where it's, you know, either selected or it's not, what I wanted was to have an effect to colorize the image. So the ones that are grayscale are the ones that are not selected. The ones that's colored obviously is the one that's selected, but also animate to that change. Give a sort of transitioning effect as opposed to an abrupt change in the UI. So I'll probably talk about these effects later, and Romain is going to talk about the reflection effect real soon now.
Okay, so this is a list. It's not a complete list of all the drawing tools provided by the Android platform, but these are some of the most common tools that you can use to create cool special effects. So everything that you've just seen, like colorizing the thumbnails, creating a gradient, creating a reflection, drawing bitmaps, this can be achieved with those tools. So we have paints, shaders, color filters, Xfermodes, that also called blending modes or transform modes, and bitmaps. We're going to take a closer look at each one of them. Paint is a very important object on Android. So if you're familiar with other drawing APIs like Java 2D, for instance, usually the equivalent of Canvas, that was called Graphics 2D in Java 2D, contains all the states, all the transformations you apply live on the canvas. On Android, it's different. The canvas itself is a bit contains only the transformations, and the paint contains pretty much all the states. So if you set the font size, the text color, the anti-aliasing, the filtering, the blending modes, the raster effect, the path effect, the mask effects, I mean, there are dozens of states that you can set on a paint. So the paint is a pretty heavy object that contains everything you need to draw something. And this is why it's very important that you don't create paints all the time in the draw method. If you're creating an animation in your app and you want it to run at 60 frames per second, but every time we draw, you create a new paint object, you're going to saturate the heap and you're going to cause garbage collection. And when the garbage collection hits, your animation will stutter because we'll have to pause your thread to perform garbage collection. So be very careful with paints, try to allocate them ahead of time, and if you look at the source code of the Android platform, you'll see plenty of great examples on how to do that. Shaders are, the name is a little weird. Shaders basically specify how to draw horizontal spans of colors. They're similar to shaders in OpenGL or in 3D in general, but not quite. They basically you can basically use them to define how to fill a shape. So if you're drawing text, if you're drawing a path, if you're drawing a rectangle, you can set a shader to draw something more interesting than just a single color inside that shape. If you want to draw a gradient, or if you want to draw a repeated bitmap, you can use a shader. So this is a list of shaders that we offer on the Android platform. We have linear gradient, just a very simple gradient. Radial gradient, also called circular gradient. We have the sweep gradient, bitmap shader, and compose shader. The way compose shader works is you give it two shaders, it will blend those two shaders together, and they'll fill the shape with that. On the native side, this is not exposed, but on the native side, you can create any shader you want. This is not exposed in the Java API yet, and I'm not sure it will ever be. But shaders can be much more powerful than those few, and if you have great ideas of types of shader we should offer, like, let us know. And we will see an example of how to use the shaders later on. This is how we did the reflection effect in the demo. Color filter, it's a simple mathematical operation that we do per pixel. we have a predefined set. There's Chet's favorite class called the color matrix color filter. It's a terrible name. We have the lighting color filter and the Porter-Duff color filter. The Porter-Duff color filter has also a really weird name. It basically lets you change the color of anything. And we have an example here on the home screen. So if I drag something over the trash can, for instance this widget, it turns red. And to turn that widget red, I'm just using a Porter-Duff color filter with a red color. The lighting color filter is not very useful. It's mostly used to change the brightness of a shape. Color matrix color filter can be used to change the saturation of colors. So the black and white thumbnails that you saw before, I believe, were implemented with color matrix color filter. Yes. If you wanted to do a CPI effect or something like that, you will use that filter as well. And once again, in native code, you can create your own color filters, but we don't let you do that on the Java side. Xfermodes, once again, a weird name. I should maybe stop saying that. Like all the names that we have for the drawing APIs are a little bit weird. So it's blending mode. And Porter-Duff, how many of you are aware of who Porter and Duff were? I like you guys. So Porter and Duff, two dudes who wrote this awesome paper. I believe it was in 1984, 82. Yeah, a long time ago. And they defined 12 blending equations that basically define graphics as we know it today. Those 12 equations define how transparency affects colors. So this is what gives you, cool 3D movies and cool graphical effects in computers today. So there's a bunch of modes. They're not all very useful. Some of the two most commonly used ones are called source over and destination out. We won't go into the details here. You can find great papers online about Porter and Duff. But the point is, as part of our blending modes, we also have other types of blending modes that you can find in tools like Photoshop or the GIMP. So the four blending modes we support are called darken, lighten, multiply, and screen. I've implemented those myself a few times, and I can never, ever, ever remember what they do. So what I do is I just launch Photoshop and I just play with them to see which one is the one I want. But they're extremely useful. So the effect of colorizing the widget in red that we just saw on the home screen, I was just using the red color and the screen blending mode. So that reflection effect, how was it implemented? So it's pretty simple. We use two shaders that we compose into a compose shader. We start with a bitmap shader, and all a bitmap shader does is take a bitmap and puts it on screen. You can do fancy stuff with it. You can apply transformation matrices, so you can rotate the bitmap, you can scale it, stuff like that. I also created a linear gradient. It's not a gradient from black to white. It's actually a gradient from fully opaque to fully transparent. It doesn't matter what the color is. It doesn't matter. It doesn't matter fancy stuff. It doesn't matter apply transfer. It doesn't matter matrices. So it doesn't matter bitmap. It doesn't matter it stuff. It doesn't matter. It doesn't matter. Create. It doesn't matter gradient. It doesn't matter. It's not a gradient black. It's actually from full to fully transparent.
He talked about 3 elements to creating the reflection. There was actually 4 that I used in the sample application that we saw. There's the original image that you have. There's the gradient that you create as an alpha mask to blend the colors through, and then you put them together. And there's an additional step that I did in the demo application to blur the reflection to give a more realistic reflection on a matte surface effect. So here you can see that I'm creating the blur by doing basically a scale down and a scale up. It's a really quick hack to get a quick blur. I'm creating the let's see, the bitmap shader. From the blurry bitmap, we're doing an inversion because we want to flip, because obviously it's a reflection, not just the same image copied down. Then we're creating the alpha gradient that he talked about, where I'm going to partially transparent to completely transparent. Then I'm creating a compositor. This does a Porter-Duff mode of dest in. This is the opposite of the one that he used, basically because it depends on whether you're going from transparent to opaque or opaque to transparent. And then finally we're setting the shader, which is going to blend that linear gradient on top of the blurry reflection, and then you get the resulting thing that you saw. And now we'll go back to the slides.
The one trick here is, so we create our paint, we set our shader that's made of a gradient and a bitmap. And then we just draw a rectangle. So we draw a rectangle that will be filled with the bitmap. We do not call draw bitmap, we don't call anything else. We just call DrawRect. And the last parameter of DrawRect is the paint that contains the shader. So if for some weird reason you wanted to create a circular reflection, you could just draw a circle instead. It will work with anything. Bitmaps. So bitmaps extremely important on Android. They are widely used throughout the system, even behind the scenes sometimes without even you knowing it. So we have two types of bitmaps. We have mutable bitmaps. This is usually the bitmaps you create. That's bitmaps you can modify. And we have immutable bitmaps. Immutable bitmaps come from resources. So if you load a bitmap from res/drawable/myprettypicture.jpg, it will be immutable, so you can't draw on it. Bitmaps also have the notion of density, and we do that to support multiple screen resolution. So if you load a bitmap from, let's say you have a bitmap in the directory called res/drawable-mdpi for medium DPI, and you run on a phone that's high DPI, we're gonna load that file. It's gonna be associated with a density of 160 DPI, and we're gonna use that information at runtime to scale the bitmap automatically. Bitmaps can be recycled, so because bitmaps can be really large objects and you don't have that much memory available to your app, sometimes it makes sense to free the memory used by the bitmap as soon as possible. So you can use the method called recycle to liberate the memory without waiting for the garbage collector. And finally, bitmaps, we support 4 different types of bitmap formats. 2 of them you should never use, which makes you wonder why they're there. Alpha 8, you should use this one, but you will never use it. It's basically used only to store alpha masks. So if you're writing a font cache for a game, or if you're doing fancy clips with arbitrary shapes, you might be using that format. Otherwise, you'll pretty much never use it. ARGB4444, as this pretty name indicates, it supports alpha, red, green, and blue, and each one of the components is stored on 4 bits. So you have no precision, and it looks like crap. Don't use it. ARGB8888, that's a good one. Full ARGB 32 bits that you're probably familiar with. You have translucency. It takes twice as much RAM as the last one, but it's the only one you should use if you need transparency. And finally, we have RGB565. So you have limited precision on colors. You don't have an alpha channel, so it works great for photos. But for anything else, you will have bending or you will have dithering artifacts. It saves a bit of memory. It's a little faster to draw, but usually the trade-off is not worth it. And currently, up to Android 2.2, when you load a JPEG, for instance, we know that the JPEG is an opaque image, so we load it as an RGB565 image. So we lose quality in the process, and it sucks. I mean, a lot of people have been complaining about rendering artifacts. So as of Gingerbread, every single image in the system that you load will be loaded by default in 32 bits in ARGB8888. And because of that, we give more memory to applications to accommodate for the extra memory usage. But the result is much better because quality is improved. Yeah, so we have those 4 different formats. You should always try to use the format that's right for you. Try to preload the bitmaps in the format that you will need at runtime, because otherwise every time we draw the bitmap we'll have to do the conversion and it can be really slow. There are 2 ways to control the quality when you draw incompatible bitmaps. So if you draw a 32-bit bitmap onto a 16-bit surface, which is a 16-bit surface is the default behavior before Gingerbread. You want to enable dithering. Dithering is a weird algorithm that basically introduces artifacts in your image to make it look better, and we'll see an example of that. So if you use incompatible images, you will get performance hits. You should avoid blending at all costs. If you don't need an alpha channel, well, don't use it. We have a special optimization in the platform. If you load a 32 bits image that's completely opaque, that's okay. We'll figure it out and we'll enable special fast paths for that. And again, render onto compatible surfaces. When you're in the onCreate method of your activity, you can call getWindow.getAttributes, and you can check the format of the window, or you can modify the format of the window, and you can check whether the window is going to be 32 bits or 16 bits. And based on that, you can load your bitmaps in a different way, or you can force your window to be in the format you want. Again, in Gingerbread, it doesn't really matter because everything will be 32 bits. So why does this matter? It matters because of this little demo right here. So what I've done in this demo is I've created this lovely picture of gradients in Photoshop. And this demo right now is running with a 16 bits window. So we have 16 bits of precision to draw in that window. And you can barely see, but if I zoom, can you see in the back, you can see like bands, you can see lines. So the gradients is not perfect. This is because I've loaded a 32-bit image and I'm drawing it onto a 16-bit surface. Basically what it does, it clamps the values to 16 bits. So it introduces artifacts and we lose the precision in the gradient. Now if I turn on, and you can actually see it really well at the bottom in the gray gradients. To limit that effect, we can enable what we call dithering. And this is with dithering enabled. So the bands have disappeared, but you can't really see, unfortunately. Let me see if I can zoom more. It's hard to tell. If you squint really hard, you might see noise in the red. Let's check the green. Can you see the noisy pattern in the green? Yeah, kind of. Okay, we'll give you the demo so you can run it. Basically, this noisy pattern is introduced by the dithering algorithm, and the idea is that when you're zoomed out, it basically tricks your mind, and it makes the gradient looks perfect again. Now, if we go to ARGB 4444, you can see crap all over the place. Like here, doesn't look good. Don't use it. If you enable dithering, it still looks like crap. Don't use it. RGB 565. So RGB 565 is compatible with the background window. So it's very fast to draw. But because we've already loaded the bitmap in 565, we've already lost information. So either we've already dithered when we loaded the bitmap, or we did not. And either way, it's gonna look okay, but not very good. If you have a 16 bits window and you want performance, use a 565 image. And if you care about quality, use a 32 bits image and enable dithering. But now, if we switch to a 32 bits window, so this is ARGB 888 without dithering, it looks great. We don't need to enable dithering. If you go to ARGB 4444, it still looks like crap. Don't use it. And the last one, here we go. And RGB 565, you can barely see, but it has the same problems as before. And this is why we switched to 32 bits by default in Gingerbread. So performance, I mentioned that choosing the right bitmap format is very important. I measure those performance numbers with the emulator, so if you try on your own device, it will be very different. And actually use the application you just saw. By default, it shows a performance counter. So you can see that drawing a 32-bit image, there's a 3x difference between drawing it onto a 16 bits window and a 32 bits window. So just because we have to draw in a 16 bits window, we have to do conversion, so that's way more code that we have to run, and it's a lot slower. And now if you look at ignore RGB 4444 and the RGB 565, so 16 bits, when we draw it onto a 16 bits window, it's extremely fast because we basically do only a mem copy. And it becomes slow when we draw it onto a 32 bits window. So the numbers are reversed with 32 bits. So make sure that you're using the right format for your bitmaps. We talked about it, blah, 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 blah. OpenGL remains 16 bits. Some of the APIs you can use with bitmaps. To create a bitmap, you have to call bitmap.createBitmap. The constructor is not public. There's a create scaled bitmap that you can use to create a resized version of your bitmap, and in the reflection effect that Chet demonstrated to do the blurred version of the reflection, he was using this API. Bitmap factory and all its decode methods is what you can use to load images. And in Bitmap factory, every decode method takes a set of options, and you can use the options to to decide what format you want to load your image in. Finally, we have copy to copy a bitmap, compress if you want to save a bitmap. It's especially useful for debugging. You can save as JPEG and PNG, use it. And recycle that I already mentioned. If you have a large bitmap that you know you don't need anymore, call recycle on it to get rid of the memory as soon as possible. And then just a couple of quick examples how you draw onto off-screen bitmaps. So here, for instance, we're going to draw text into a bitmap, so we just create a paint. We set anti-aliasing, it's very important, otherwise it will look bad. We set the text size, we create a new bitmap that's 256 by 256 pixels, and we choose the configuration ARGB 8888. That's a 32-bit bitmap with transparency. And then to draw on the bitmap, you need a canvas. So you just call new canvas, and you pass the bitmap that you want to draw onto. And then you can call any method on the canvas, and it will modify the bitmap automatically. And once you've created a canvas, it doesn't have to remain associated with that bitmap forever. You can call setBitmap, I believe, and so you can retarget the canvas on 2 different bitmaps. You can create the canvas only once and retarget it, so you don't have to recreate it every time. If you want to copy a view, so if you want to take basically a screenshot of a view into a bitmap, this is a question that comes pretty often on mailing list. This is the code you have to run. The code up there is not always necessary. So if the view is already on screen, you won't need the first few lines. Basically, those first few lines are, this is how you force a view to be measured, so you know how big it is, and that's how you do the layout on that view. If you don't do that, the view will have a size of 0 by 0, and when you draw it, it's not going to work really well. Calling measure will also let you know how big the bitmap should be. So once you've measured and laid out the view, you can create a bitmap with the dimensions of the view. You give it the configuration you want, and then very similar to drawing anything else. The only trick here, line 11, we call translate, and we translate by view.getScrollX and getScrollY. So if you're drawing a view like a scroll view or other views like that, even a text view, they have an offset called scroll that they use internally, and you have to take it into account. Otherwise, you will see the wrong part of the view. And finally, another way to draw a view into a bitmap is to use an API that we provide called the drawing cache. So you just call view.setDrawingCache enabled true, and then you call getDrawingCache, and you will get a bitmap. Be very careful with that bitmap. That bitmap will be used by the system, so do not recycle it. Do not keep a reference to it thinking that it will stay in memory forever. If you need to keep it around, make a copy. And when you're done, call destroy drawing cache. Finally, animations.
Finally, indeed. Oh, you wore me out about all that graphic stuff. So, I joined the team about 6 months ago to work on animations, which happens to be what I've been working on for the last few years, just not on Android. So tonight I wanted to talk mostly about the current state of animations, and I also wanted to give a very brief glimpse of where animations are going in potential future releases. So why do we care about animations? I care because I'm a graphics person and I think they're really cool. But I think you should care because it actually enables better user experiences. I think it's really easy to get lost in user interfaces, and it's easier for your users to get rather upset because they don't understand what's going on. There's a lot of information to process even on these tiny little screens. So the more that we can help the user along as they use the application, the more they're going to understand what's going on in the application, the more they're going to like the application, and the more money they're going to pay you for it. I firmly believe that. So the whole point to animations, to the kinds of things that I try to enable in the platform animations, is helping to keep the user engaged in the experience, help keep them connected to what's actually going on the screen. So there's an animation superclass in the current SDK, and it has all the common properties that all of the animations share. You have a duration, how long is this thing going to run for, how long do we want to wait before we kick it off in case we're choreographing several animations together. You want to stagger some of them. We have the ability to repeat, and that's repeat as in a loop, or also repeat in reverse. You can repeat infinitely or a certain number of times. Easing. Interpolation is so important. Don't forget about it. We actually do nonlinear interpolation by default, so for the most part you don't need to think about it, but depending on what you're doing in your animation, it's terribly important to think about the kinds of behavior that you want in that animation. Is the view going to accelerate over to the right? Is it going to decelerate? Is it going to ease in and ease out? If you're simply doing a fade, nonlinear motion doesn't really kick in. It doesn't really matter that much. But for anything that's actually moving on the screen, definitely use nonlinear motion, because otherwise it looks like crap. Yeah, I think that's Romain's word for everything. Yeah, it's French. Pardon my French. And then we have the ability to fill after and fill before, which is basically saying, okay, do I want to keep this value after the animation is complete? Do I want to move the view over to the right and then leave the view there? Which is problematic for reasons I'll get into in a minute. So we have a few different animation types. The basic state of animation in the current SDK is we cover the basics, right? We allow you to move stuff. We allow you to rotate it and scale it, sort of do the canonical transformation stuff. We also allow you to fade it, and we also allow you to sequence, so create a choreography of animation. So where I'm going to move this thing over, and then I'm going to fade it out. And sort of sequence things together, multiple complex animations. There's also the ability to crossfade, and that's what you saw before in the thumbnails for the reflection effect. As I went from the grayscale to the color version of the thumbnails, that was using a crossfading effect, which I'll show on the slides a little bit later. And then finally we have layout, and this is basically the ability to say, here's the sort of template animation I want you to use for this layout of objects, and when the layout actually arranges its children, it's going to fire off a number of these template animations and stagger them by some predetermined delay, so that it can sort of lay the children out in sequence instead of just popping it onto the screen. So the transform animations all sort of take this form. You set, well, this is some XML code. You can also do this programmatically in Java. And you basically give it the properties. So this is saying, okay, I want to move from a y of 0, and I want to give it a % value. So there's different ways to specify the dimensions, or the percentage, the fraction of your current size, or the positions relative to the parent. There's different ways of actually specifying the units for the animations, and then you give it a duration, or it's got a default duration of, I think it's 300 milliseconds. So the weird thing is, and this kicks in if you're ever going to do a fill after, if you want to move the button from here to there, and then I want it to do a fill after equals true, and then you go to click on the button and it doesn't click, and you file a bug report because I'm clearly clicking on the button, but it turns out you aren't. You're clicking on the space where the button is drawn, not where the button is. The button still lives here, right? Sort of an important detail to note. If you actually want the button to be over there, fine, run an animation and then actually move the button over there physically, because otherwise, if you click in this empty space where the button used to be, it's going to highlight like you're clicking over there. It's kind of a bizarre thing, but animations in the current SDK are all about making things look animated as opposed to actually animating the objects. What's going on in the code, in the architecture that Romain was showing you earlier, the view group, the container of the children, is actually responsible for drawing the views, and it detects whether that view, that button, has an animation running on it, and if it does, it will draw the button in the appropriate place according to how the animation has changed the transform of the button. But the button doesn't actually exist in this other place, right? Sort of a nuance there which you probably won't care about for the most part, but if you ever run into an artifact where you think you moved something due to an animation, the truth is you probably didn't. It just looks like you did. So fading, here's one of my favorite things about the animations. Alpha is actually a property on the transform object, which I think is just bizarre. But it was a convenient place to stick a property, and there it lives. You write an alpha animation by giving it the property from 1 to 0. This is going to be a fading out animation. You give it a duration, or you use the default. Again, this is not the translucency of the view, it's the translucency that the view is going to be drawn with. Subtle nuance probably doesn't matter for the most part, but it's an important thing to keep in mind if you use a lot of animations. Sequences are very useful because typically an interesting animation is not just going to consist of, well, I'm going to scoot this thing over. Well, hopefully you're going to scoot it over with nonlinear motion, right? Timing interpolation, good thing. But maybe you actually want to scoot it over and then fade it out. Or let's say you have some complex container animation where you want to add an item into the middle of the container. Well, you probably want to make room for it by moving things over, and then you want to fade this other item in. Well, this is a sequence of animations. You're not just moving things, you're actually moving several things, maybe with a stagger between them, and then fading something in. And animation set is what enables you to do that. So in XML code, you would say set, and then you'd say, well, here's a translate animation with the following properties, and here's an alpha animation with the following properties to fade this thing in. And crossfading is the effect, I mentioned this before, that I used in the thumbnails. So this is not actually using the alpha property on views or the transform that I was talking about earlier. Instead, you create this transition drawable. These are two graphical objects. One is in back, one is in front, and you basically tell it which one should be the visible one, and it'll animate to that state. So what I did for the thumbnails was to create a color matrix color filter, my favorite class name, and then I created two drawables. One had a saturation of 0, and that was the grayscale one. The other one had a saturation of 1. And then I put those in as the two drawables in a transition drawable, and then I would simply change the state based on when you clicked on the thumbnail in the gallery, and it would say, okay, transition to the front one or transition to the back one, and it automatically handles the animation for you. And finally, layout animations are about staggering some template animation for every child in a view. For instance, there's a standard one that's declared in the current framework that does a transition for a grid layout, and you basically give it the animation properties itself, and you give it the layout animation properties, and this gives it how much you want to stagger between each of the animations as it runs, and it sort of magically does the right thing. So there's a lot of capabilities of animations in the platform today. Most of them are sort of automatic. They do some very simple things very well. It's pretty easy to declare the things and to trigger them off, and they do the right thing. They're not necessarily the best at flexibility, and so if you want to, for instance, animate something about a view that doesn't happen to be a transform property or some translucency property of the view, you're pretty much out of luck. You're down to creating custom animations. There are different ways to do that, but you can, create a handler, basically, create a new UI thread or new handler on your UI thread, fire off timing events there, and sort of manually change things along the way. But maybe there's a better way to go about things. So a couple of performance tips to keep in mind. Set drawing cache enabled true. Romain mentioned this earlier as a way to get the bitmap of a view. It's also a way to tell a view to represent itself as a bitmap. If you're doing a complex animation with let's say a complex view and you really don't want to re-render it each time, maybe you just want to tell it to represent itself as a bitmap so that during the animation all it's going to be doing is copying a bitmap around.
And actually the drawing cache is so useful that we use it in the system to achieve good performance all over the place. So for instance, every time you scroll a list of items, as soon as your finger touches the screen, we transform every item on screen into a bitmap, and then when you scroll, we just move the bitmaps. And when new items comes on screen, we just recycle the bitmap and so on. And we just use this set drawing cache enabled API. So it's very efficient. It's widely used by the system, so it works really well.
Actually, do you want to talk about the animation cache?
Animation cache. So we also have what I just mentioned is what we call the scrolling cache. You can disable it for some reason if you don't like it. If you want your app to be slow, you can force the system to do that. We also have the notion of animation cache. So on ViewGroup, if you turn the animation cache on, automatically when you run animations like a layout animation, we will take care of enabling the drawing cache for you on all the children. And I think it's disabled by default.
Okay, so in the current animations, like I said, you can do a lot of stuff very powerfully and very easily, but there are some problems. One of them is that there's only specific things you can do. You can translate, rotate, and scale, and you can fade that view, and that's really all. Right? There are more things that views can do, but you can't really animate those things easily. You're down to writing a lot of custom code, and some properties of views you can't even necessarily get at to alter along the way. So you're down to writing a fair amount of code to do what should be simple animation. So maybe we could make things a little bit more flexible. Also, you can't animate arbitrary properties. If you want to animate something about a drawable, let's say you have I don't know, a ball with a radial gradient that you want to bounce up and down, and you would like to animate the color at the same time. This is my favorite canonical type of animation to write. You cannot animate the color of that drawable. There is no way to do that in the system. This is not a general animation system that lets you target any property in the system. Instead, it handles specific types of actions, which are basically everything I just talked about in the last 5 minutes. And finally, if you have a custom object, well, you're totally on your own. We don't know anything about that custom object, so how could we possibly animate it? We can't even figure out how to animate some things about views and drawables, which we do know a lot about. And then there's finally the other problem that I already mentioned, which is you're not actually, when you run one of these animations, you're not actually changing the view itself. All you're changing is how the view is displayed on the screen, which is great in most cases because, frankly, animations are little movies that play. And if all they are is a little animated segue between this and that, then where the view is displayed compared to where the view is irrelevant, right? You're just going to play a movie and then get on with your life. But sometimes it's a problem. I wanted to animate this thing over there, and then I wanted to interact with it, and you can't. So wouldn't it be nice if that was actually the same thing, if animating the view was the same as actually changing the view along the way? So some people on the team have been working on a new animation system, which I'll call a property animation system, and you can basically say something like, I want to animate the X property on this object, right? And then it would actually change that X property over time. Fairly simple concept, but it's not in the current SDK. Instead, it's something to evolve to. And then if you say, well, I want to animate X, then it could basically look onto that object and say, okay, someone wants to animate your properties. Do you have a setter and getter that I can use to manipulate this object over time? So first we'll read the disclaimer. This API example does not represent a commitment to any particular implementation or interface in any future release if there were such a release, which is not guaranteed. All right. This might be sample code in some future release, which doesn't exist, that could do the stuff that I'm talking about. So in XML, you could say something like, okay, well, here's this object animator object instance that I'm going to use, and this is what I'm going to animate. I want to animate a property called X. That's on some target object that's not specified here. And I want to go from a value of 0 to a value of 100. In code, the way to do that in Java code would be say, okay, let's create a new one of these objects. We're going to target this object here, some shape object that happens to have an X property, a setX method. Or actually, this one's animating alpha, so it's going to need a setAlpha method on that object. And it's going to go from a value of 0 to a value of 100. And then we're going to start the animation. Fairly simple concepts. They exist in other platforms. This is not radical new stuff, but it should help in the flexibility of animations on the Android platform in particular. More information, more and more and more. In case we didn't talk enough tonight, you can find out more information certainly on the developer site for Android. Download the SDK, download the tools that you're seeing tonight. You can reach us or follow us on Twitter if you're into that. And these are our blogs. Romain posts a lot of very pretty pictures and occasional code. And I haven't yet posted Android code, but it's going to happen real soon now. The demos that we're showing tonight, I expect most of them to be out there in some form, articles or videos, sometime soon on one or both of these blogs.
Yeah, so you want an easy way to skin your app? Someday, maybe. I know, it's something we talk about very often. We're still not sure on how we want to do it. Because we would like to solve many issues around that. It's not just changing the colors of the asset. It's also supporting multiple densities, multiple resolution, and all that stuff. So we had ton of ideas like using some sort of SVG at runtime, maybe compiling SVG like in the SDK in your app, where you could do the skin. Why don't we draw everything as primitives? So that's how Swing worked. The reason is performance. And we could use then drawing caches to get better performance, but then the problem is memory usage. So that's our current trade-off. And as devices get better and better, we'll go towards more and more modern solutions. But for now, that's our best solution. And actually, we have a nice resource caching mechanism where when you load drawables, if you load like 100 drawables from the same asset, we actually have only one copy of the asset in memory, and so it's all about memory usage. We're still, we have awesome phones like the Nexus One, the Droid 2, that kind of phone, but we still want to be able to run on stuff like the T-Mobile G1, like the HTC Wildfire, like phones that are not the super phones of today. So the question is about what we're going to do with density and screen sizes for tablets. We will see when it happens. But more generally, we have the notion of density. So we have low DPI, medium DPI, and high DPIs. And then we have notion of a screen size. So we have small, normal, and large screens. So you can have a large screen that's also HDPI, but you can have a large screen that's medium DPI. So there will be some combination of those things for future devices, if they ever exist. We're not doing hardware acceleration? Well, it depends what you're talking about. Once again, window composition is hardware accelerated. If you use OpenGL, it is hardware accelerated. If you're using the 2D drawing library, it is not right now. And the reason why we're not doing it is because, first of all, OpenGL until OpenGL ES2 was very ill-suited for that kind of work. Like, you can't really do precise, high-quality 2D graphics with it. It's possible with OpenGL ES2. It might not always be better to implement with OpenGL, and actually Chet worked on 2D hardware acceleration with DirectX for Java 2D at Sun, and he knows what I'm talking about when I say that it's not always better or running on the hardware. Like, if you draw an arbitrary shape with anti-aliasing, it can be very expensive in GL. It's something that actually I've experimented with myself before we released Android 1.0. Wasn't possible at the time. We're still investigating. If it's worth it, we'll definitely do it. But in our experience, most of the time, I'm not saying always, but most of the time, drawing is not the bottleneck in applications. It's very often blocking the UI thread, accessing, like, it's blocked on I/O or network. But yeah, if we need to go there, we'll go there.
It turns out the OpenGL API and the GPUs were really crafted for running Quake really, really well. So I think as long as you have a UI that looks exactly like Quake, you could totally rock with GL. On typical GUI 2D primitives, the equation is not quite so simple. I think that's all the time we have, so I think we're done. Thanks.